Hi everyone, perhaps we just start. Before we start the lecture today, a few questions. Can anyone access the laptops to recording? Any other? Sorry. So I assume Panapto's access is working well, right? I just don't know why the slide is not shown in the projector, just not working. Yep, it works now. Okay. Yeah, so I assume the Panapto access is okay for everyone. So this is the thing I want to check. Before we start the new materials, there are two things I want to explain. The first one is last time some students are saying the concept of depth-wise convolution is not so clear. So in here, try to introduce this a little bit more. Like in here, this is the standard convolution. So let's say we have one filter here. So this filter actually contains, let's say, this input feature map in previous layer has 4 channels. So which means in standard convolution, we actually have 4 set of weights totally, and each set of weights is corresponding to one channel. And we do this convolution one by one channel of filters according to corresponding to the one channel in the input feature map. We do convolution, and we do this channel accumulation to accumulate all the intermediate input feature map together, and we got this output feature map. So that means the number of filters is equivalent to the number of output feature maps in the next layer. So this is convolutional neural network standard one. So you can see inside one filter, there are multiple channels. In depth-wise convolution, rather than having multiple set of channels for all the input channels, so we only have one channel in one filter. So which means there's no channel accumulation, and we just take one filter, multiply with one channel, and get one output feature map. So this is critical in our tutorial questions. I hope this is clear to you guys. So yep, no more misinformation. And the other thing is, I think there's a great question in our STEM system, which is the flops count. So I changed our slide to make clear which is the flop counts of fully connected layer. So when I introduce this concept, I use the matrix multiplication as example, but student might link this explanation to the linear layers with bias addition. So in here, I make it more explicit. So we actually have two additions. One is the addition for accumulation, where you do the matrix multiplication. And the second is if you have the bias addition here, so you have another addition count, which is here, and the total flops is exactly equaling to this formula. So this is another thing I want to explain a little bit more in last lecture. And today's lecture, we will start the introduction to transformer architecture. Last time we stopped at this slide, right? So this is the table from TPU V4. So they try to provide some information about the internal changes in terms of the workloads in Google TPU. And they found transformer is becoming dominant at the time of 2022, even before the GPT time, ChatGPT time. So this is the reason why in this lecture we will introduce transformer. But before introduce transformer and its backbone attention-based neural network, we will introduce recurrent neural network. So so basically the recurrent neural network is designed for time-dependent data analysis or sequential data analysis. So in many real-life applications, you will see a lot of tasks. They actually involve some information, some time-dependent information. For example, I mentioned on Monday. So we have the video understanding task. We actually need to extract the motion information from multiple image frame to do some action analysis. So many applications, they actually need the time-dependent information. And also for sentence generation for language. So you can see if, okay, here is a sentence. Machine learning system module is amazing. So I want to spend more time listening. So basically, if you're able to extract some information from previous, what we call here as prompt. So if you are able to kind of extract some key information from your prompt, which is kind of time-dependent information, you can kind of have more information for your generation. And the key idea of recurrent neural network is exactly designed to keep a hidden state, which can keep evolving and propagate from time to time, and such that they can kind of enable the model to remember the previous inputs and memory. And another thing I want to mention here is memory now is becoming a very core topic in large language model, because you can see a lot of research is discussing agent memory. So the memory is becoming more and more important because when, let's say, large language model, they are deploying in our real life. So in most of cases, the inputs is kind of in a streaming setting, which means it's like day-to-day inputs coming. So they need to kind of store short-term memory, long-term memory, and external memory. So this is just for the latest research topic, agentic memory, and we will introduce later in our lecture. But let's coming back to a recurrent neural network. So recurrent neural network, the structure is showing the slide. The core idea is just we keep managing or updating a hidden state, and we have these input state, and we have this hidden state and output. So we use different matrices to do the linear transformation. For example, this is the very basic version of recurrent neural networks. So we have the weight matrices U, V, W. So we just, the computation involved in this process is we first use this linear transformation to multiply a U with the input and V with the hidden state. We add them together, we apply a sigmoid function. And then for the output generation, we apply a softmax before we apply softmax, we'll apply another weight matrices to the hidden state. So this is a very basic version of recurrent neural networks. And as I mentioned before, this module is not going to teach you like how we design this algorithm. So mainly we just help you to understand what is the computational pattern, what is the main computation and the memory access involved in all these mainstreaming deep neural networks. And when you try to, if you look at this structure, we'll try to unfold it. You will look at how it tries to keep like updating the hidden state. When we have the input, you update the hidden state, and next time we have new input coming in, so it will kind of receive input from the previous hidden state and keep updating the current hidden state. However, there are several limitations in recurrent neural networks. So one thing is it's not able to capture the long-term sequence. Like just keeping one hidden state is not enough. So this is the main problem of initial version of recurrent neural network. So there are many variants proposed after the initial version of recurrent neural networks. And in this module, we will briefly introduce this LSTM. I guess many of you already know this, but we will not go into detail of it because this is not the focus of this module. We just need to know what it is and like how transformer is proposed to overcome these drawbacks. So basically, the computation of a recurrent neural network is, instead of just keeping one hidden state, it first introduces multiple gates. So they have the forget gates, input gates, and output gates. All these gates are basically just different linear transformation. And they introduce the cell state. So they have the input node, cell state, and hidden state. They kind of have more complicated computation here, like they have 10H, they have sigmoid, and they have different matrix multiplication here. So you can see the states that propagate to the next prediction is not just hidden state, it also has a cell state. And what's more, instead of just use one U and V in previous slides, we have more different like activation functions and different weights for the information processing. However, this LSTM is kind of, to some extent, mitigate this long sequence problem, but it's not totally address the problem, address the short-term memory issue. And another problem of LSTM is the sequential data processing, which means, let's say you have input. So there's some data dependency among different inputs. Let's say you have input X put into here, and you process all this computation, and you get the hidden state and cell state. You pass all these hidden state and cell states to the next generation. So they kind of, the current generation is depending on all the previous generation. So this is kind of inefficient in terms of computer system because we are not able to increase the parallelism for processing. So these are two limitations in recurrent neural networks. So attention neural networks is proposed exactly to address these two limitations. So as you can see, the sequential processing in recurrent neural network make its processing speed very slow. And the second is it's not able to capture the long-term sequence relationship. So the idea of attention is to allow the models to attend any part of the sequence directly. So later on in this module, we actually keep a key and value vectors for each position or each token. So when I say token, it means, for example, a word in a sentence. So it actually explicitly catch or have the different like key and value vectors for each token. And this is the idea of attention is not new. Even before the large language model, it was already used in 2014 for machine translation. And you can see this paper later on if you are interested. And now the attention-based neural network has become the fundamental building block in existing generative AI. So the next slide, we will introduce what is the computation involved in attention-based module. So the picture here shows the layer structure of attention. So basically, you can see for the input tensor coming inside, so we will have 3 linear layers, right? So to help you to understand more about the mechanism, so in here I also make an example in the right-hand side. So for, let's say we have 2 words, thinking and machine, which are 2 words. So as I mentioned in our last lecture, so we have the pre-processing, which kind of map our sentences to different sets of token. So, and this token will be processed by tokenizer, which map the token to embedding. So here, the thinking and machine, first, they are represented as the embedding vectors, x1 and x2. So this is how we process all this information. And you can notice here we have 3 linear layers, right? So the next step is basically just use the linear projection to kind of transform the x1 to q1, k1, v1. So the q means the query, k means key, and v means value. So we kind of use 3 linear layers to project 3 different vectors. So, and then we comes to the key computation of self-attention. So basically, the first thing we will do is we will first multiply query with key, which is try to capture the relationship among different tokens. For example, here we multiply Q1 with K1, Q1 with K2. So K2 is the key of the second token, right? The second embedding vectors. So after getting this, we have we do a scaling, and later on we will explain why this scaling is so important. And we get these 2 numbers, and we do softmax, and we multiply this normalized vector after softmax with value vector, so we get the final outputs. And at the end, we have another layer, which is called layout projection, which try to kind of project the hidden vector back to the similar dimension as the input tensor. So which in this way we can just stack multiple layers together without worrying about different dimension of among different layers. So here I try to plot the layer structure of self-attention layer here. So let's say you have QKV. So you first do the matrix multiplication among QK, and you do scale, as I just mentioned before. And you do masking, which I will explain later, softmax, and another matrix multiplication, which means the score, the attention map, will need to multiply with the value to get the weighted outputs. So this is the computation involved in self-attention module. And what I want to mention here is the use of attention mask, because this is part of the reason why attention module is so powerful and flexible in controlling how different tokens can influencing other positions of tokens and how to extract information. So in here, let's say in this slide, I summarize 3 different patterns of attention mask. So first of all, when we say mask out the attention mask, which we mean, let's say this is the attention score we got after multiplying Q and K. So what we need to do is we will apply the negative infinity in some entries. And the effect is we apply this before softmax. So we can kind of make all these numbers as 0. So we kind of eliminate the effect of all these tokens. And yeah, so this is 3 different attention masks. So the first one is called fully visible mask. So it's very powerful if you want to extract the global context. And one thing I want to mention here is it means the token in previous days is able to capture or see the token in the future. So it's basically, it's able to... Yeah, sure. No problem.
It's too much flat. Thank you.
Yeah. So first is the fully visible attention mask. It's able to extract the global attention. So your current token is able to see the token in the future. So it's very powerful in some tasks like text understanding, and also in like any computer vision task. And you can see nowadays there's a very, very popular model called VIT, Vision Transformer. So they use this fully visible mask attention a lot. And this is the first attention mask we introduced here. And the second is called causal mask, which means, for example, here, this is your input sequences. And for each input sequence, you are only able to see your previous tokens. Let's say X3 here, you're actually not able to kind of see the Y3, Y4, and Y5. But I think I plot this wrong, but yeah. But anyway, so the core idea is the input sequence is not able to see its previous token. So this kind of introduce a causal effect, which means, okay, the current token generated is not able to see the future token. This is very useful in some tasks. So like what we said later, the text generation. And people later on realize only the fully visible pattern or the causal pattern, they are not enough. So people tend to use the causal with the prefix, which means, let's say you have an attention mask. You're actually not, you kind of split this attention mask into 2 parts. The first part, you use the full visible attention, and the second part, you use the causal attention. So it kind of more natural for some real applications, like you are able to let's say you have input prompts, you have the question, and you try to answer all these questions, and you kind of set the fully visible mask on the question provided by users, and you kind of use the causal mask to do the autoregressive generation, which kind of force the causal mask. So here I put putting everything together. Now we have this attention mechanism, which is able to capture different relationship among tokens. So here, let's say we have a single head attention module. So using this powerful tool, so actually if you have access to my slides, I put link 1 and link 2. So it kind of helps you to see like how with the single head attention, how we capture the relationship among different tokens. For example, when this didn't token try to multiply with different tokens in other position, so you will realize it has the strong relationship with the because. So this means it's able to extract the keywords from different position with your current token. And all these are enabled by the mechanism I explained before. So you kind of have the key value vectors to catch all the intermediate activation results, and you try to do some analysis and comparison to extract the relationship. Let's say we have the single head attention. Now, the original paper, Attention is All You Need, they kind of introduced the multi-head self-attention. So in here, I also put some example to see what does it mean. So this is the attention map of a single head attention. You can see we only have the one vector of attention map because we only have single head. And the idea of multi-head attention is, let's say we have the QKV, and we use multiple set of linear layers to get the multiple set of QKV vectors, and we put each set of QKV into this self-attention module. We do it independently, as I just introduced before, and at the end, we concatenate them together, and we do a final output linear projection to get the final outputs. And you can see this is the attention score extract by this multi-head attention. So this different color actually representing different heads. So different heads actually is able to kind of capturing the relationship under different semantic contexts. For example, here, like we use the same didn't. So we try to plot the attention map of didn't with all different tokens and under different heads. We can finally have different kind of relationship provided. So this kind of they are all representing different semantic contexts. So this is the basic computation of multi-head self-attention. So one thing I want to mention here is I found a very good online resources, which when you click, I think it's one of perhaps this link. So they actually provide a very detailed explanation of how a transformer works, if it's still not clear to you. And this attention mechanism actually becomes the building block for or the basic backbone or mechanism for different blocks. So the first one is the encoder block. So encoder block means we use the fully visible mask in the mask attention. So this encoder block, as I mentioned before, is widely used in different vision tasks, like vision transformer. And later on, we will introduce for the initial version of transformer, they also use this encoder block to extract or to extract the information or do the understanding task. And the second one is decoder block, which means we use the causal mask during the attention computation. And it's able to capture the autoregressive dependency by forcing the causal pattern, and it's suitable for task like text generation, which is generate one by one, and the current token is not able to see the future tokens. And we also have different combinations based on these two basic building blocks. So if you can see. As you can see now, most of the language model, they are different combination of these two blocks. And we will introduce this one by one. The first one is, as I said, the initial version of transformer architecture, which is called encoder-decoder architecture. So basically what they did is, if you look at here, so they have an encoder, right? They have an encoder at the beginning to do some processing to extract the information for example, the text understanding, and they kind of feed the extracted intermediate result to the encoder for autoregressive generation. So they also adopt a mechanism called cross-attention. For example, if I have a sentence input here, so I use the encoder, let's say here I use 5 encoder blocks. I do it one by one, so I do a forward pass, right? And after this forward pass, it will generate 5 layers of K and V vectors, right? And then after all these 5 blocks of encoder, we will kind of feed all the cached key and value vectors to each corresponding decoder. So basically in encoder-decoder, we have 2 basic part. Left part is the encoder, and right part is decoder. And we do this cross-attention. And the computation is shown in this formula. So as you can see, this is very similar to the computation of self-attention we introduced before. The only difference is for key and value vectors, all this kind of vector is coming from the encoder. So this is very initial version of transformer, and people later on realize this is not so efficient, and we need to tailor it to different applications. So people then propose another transformer architecture, which is called encoder-only architecture, which means we kind of remove all the decoder layer, and we just use this encoder-only architecture for example, the image recognition, object detection, and as you can see from the vision transformer, as I mentioned before. So it's very powerful to extract the bidirectional relationship, and it's very suitable for let's say text understanding, summarization, and any vision task, because they need the global context. However, it still have some limitation. People found this kind of architecture is not able to perform very well in autoregressive generation task, for example, like the question answering. So especially in the streaming setting, let's say you have your mobile phone, and let's say you have different requests sending to your data center. So kind of you have, let's say, 10 pieces of data per second sending to your data center. And for this encoder-based architecture, it needs to wait until all the sequences are ready to start the processing. So this kind of waiting time is very long. So this is one drawback of encoder-only architecture. And at the same time, it's very computational expensive, because it kind of involves the quadratic complexity when multiply if you can see this fully visible mask, it actually needs to multiply all the input sequences with all the other tokens in this position. So it if let's say you have n numbers of input tokens, so you need to multiply these n sets of embedding vectors with another n sets of embedding vectors. So the complexity is just n squared. So it introduces quadratic computational complexity. And later on, people realize they can explore what we call decoder-only architecture, which is the third architecture introduced here. So basically, the idea is we only use causal mask across the whole model. So, but this is still not very efficient, especially when you have, let's say, you will have some context. Let's say question answering. For the question, it's still better to keep the visibility for the full question, because we need to extract information and get more context. So based on this encoder-only architecture, a more reasonable design is the final answer we have here. It's called prefix decoder-only architecture. So it's also the backbone of most of existing large language model. So basically, they use the attention mask of this prefix decoder-only architecture is exactly what we mentioned here, the causal with prefix. So instead of have two separate model or two separate parts as encoder, decoder, so they try to kind of unify this encoder-decoder architecture by just using one decoder layer, but to enable the fully visible part from the encoder-decoder architecture, they try to modify the attention mask of the decoder. So as you can see here, if let's say x1, x2, x3, they are questions, so we just put the full visible attention mask on all these prompts, all these questions. And when we do generation, we can just generate one by one by one. So this is kind of basic mechanism of the existing large language model. And so if you can see the computational flow is, it basically has two stages. The first stage is prefilling, which means, let's say if you have your question, you have x1, x2, x3. So because the attention mask is fully visible, so you can actually process all of these input tokens in parallel. So this is the first step. So we will do prefilling. So we got this x2, x3, y1. So this is prefilling stage. And the next stage is what we call decoding stage, which means once we kind of prefilling or processing all these context or question, context-rich questions, so we'll kind of do this autoregressive generation to generate token one by one, and this is what we call decoding. So beyond large language model, there are more other efficient models coming out in recent years. So one of them is called diffusion language model. So the basic idea is, or the core motivation of the design of diffusion language model is, in traditional large language model, in the decoding phase, as I mentioned before, is still, the generation is still token by token, right? It's still autoregressive. So in that case, we will still have data dependency. So the generation of next token needs to depend on the completion of the previous tokens, right? So it's kind of affect the processing speed, this data dependency. So they kind of introduced another model called diffusion language models, which means, let's say I set the number of output tokens as, like, let's say 256, and we just put all these mask tokens together. So mask token is kind of special token, which means they represent kind of the randomly generated sequences, and they just put these mask tokens all together in parallel to these diffusion models. And they try to do kind of what we call denoising process, which means after different iterations, it tries to remask or mask out different output tokens. For example, here, in the first iteration, we put all the mask tokens, and at the end of first forward pass, so we kind of decide, okay, the first token and the third token, they can be generated. So this kind of parallel processing is actually enable very fast processing speed, because all the tokens can process in parallel instead of during a generation in our large language model. It's one by one by one. It's talking a lot in this year, this diffusion language model. If you can see, if you click this button, they have a very, very amazing demo here. So they can achieve nearly 1,500 tokens per second, which is much faster than large language model. But it's still in its very early stage. The reason is its algorithmic performance is still much lower than large language model. Even it can show some comparable performance in some structured generation tasks, for example, coding. But it's still like behind the large language model. But it's kind of becoming a very promising and active research direction. And the reason why I mention here is I think this model actually has a potential for multimodal generation, because this diffusion model, this architecture to do this denoising is only applicable on the image generation task. So if we can merge the text generation and different multimodal generation into one unified diffusion language model, that kind of can improve the efficiency of our algorithm. And you can see, I think Princeton released their model called MADA at mid of this year. So they kind of try to unify different modality using one unified diffusion language model architecture. And there are more and more efficient variants. For example, Mamba. Due to the time limit, we're not able to cover in our main lecture for Mamba, but we will cover this in one of our reading groups if we have time. And the key idea of Mamba is, as I mentioned before, for a transformer, they basically have quadratic algorithmic complexity. So for Mamba, so we actually have the linear type complexity. So it can actually reduce the algorithmic complexity a lot. And you can see in some tasks which involve long-term time series relationship, Mamba is actually good. And one last model I want to mention here is the loop transformer. So here I put the paper. If we have time in one of our reading group, I will introduce later. So the key idea is in transformer, we basically stack multiple layers together, right? Let's say we have 24 layers for, let's say, 7 billion models. And the idea of this loop transformer is they just keep one layer, and they keep iteratively process this one layer again to process different to generate different tokens. And the advantage is low parameter counts and memory footprint. But the disadvantage is very similar to the disadvantage of Mamba and diffusion language model. Their algorithmic performance is still much lower than the standard large language model. So this is what we cover, attention-based neural networks. So we still have 10 minutes to go. So we will introduce the last part of our first lecture, roofline models. So as you can see, we have different models emerging and different model architecture, and why algorithm developers design these modules, these model architectures, is not the focus of this module. We only focus on how the computation is processed and how we can optimize this computation on a target platform. And if you look at all these different variants, like encoder only, decoder only, and Mamba, and like diffusion language model, you will realize the core computation is mainly just matrix multiplication, followed by different, for example, element-wise operation or different activation functions. So, and in one of our tutorial questions, we will ask you to analyze the flop count of different components in transformer, and you will realize nearly 90 or over 90% of computation comes from this matrix multiplication. So that's the reason why GPU is so useful in deep learning. And as the machine learning system developer, what we care about, as I mentioned before, is not the model architecture, it's the performance on the target platform. However, there's a challenge because I mentioned before in our last lecture, this is the golden age of computer architecture. There are many hardware available in the market. Like we have GPU from AMD, Intel, NVIDIA. We have TPU from Google. We have NPU from different like Samsung, Qualcomm. So they have different spec. So one thing we need to do is how we can choose the best hardware target hardware platform for our algorithm, and how to further optimize the kernel, or let's say if you are targeting on GPU, how to optimize the kernel design of your algorithm on a target hardware. And this challenge is not just for the wide range of hardware platforms. It even is also if you look at the evolution of GPU architecture, let's say over the past few decades. So at the beginning we have Tesla architecture. This is NVIDIA GPU. So and later on they introduce kind of different architecture like Fermi, and then the latest one is Blackwell. So they all have different specs. They all have different architectures. So as I mentioned before, machine learning system developer, we need a tool. We need a tool to help us to understand where is the bottleneck, and we need a tool to understand which hardware is suitable for the target algorithm. So this is the core of this module. And roofline model is the first model or first tool we introduced in this module to help you to understand how to analyze the performance of your machine learning algorithms on the target hardwares, target hardware platforms. And in our lab session, we'll also introduce several tools which you can use to profile, to actually have some very precise and in detailed analysis on your performance on your codes. But here, let's us just first introduce this analytical roofline model. It's very you can say this is very early stage analysis to help you to analyze your performance. So basically, what you have is to draw this roofline model. You first define the x-axis and y-axis. So the x-axis is what we call algorithmic intensity, which is measured by the number of operations per byte. And we will use an example introduced later to explain how to get this algorithmic intensity we call operational intensity. And for the y-axis is actually the performance, which means the flops operation per second. And how to draw this line? So basically, we just need to draw two lines. The first line is this slope line. And this slope line is determined by the bandwidth of your computer system. So which means, because in here, the slope line is determined by the bandwidth times the algorithmic operational intensity. So once you got this 2D plot, you basically just, let's say, your bandwidth is, let's say, 200 gigabytes per second, and you multiply this with the y-axis, and you can get a line crossing the origin. So this is very, very simple, right? So this slope line is very easy to plot. You just need to know the bandwidth, and the slope of this line is determined by bandwidth. And you also need another line, which is the vertical line at the top. So this vertical line is kind of dependent on the amount of compute resources you have in your compute system. Like for GPU, if you look at the specs, they will say, okay, this is like 100 teraflops per second GPU. So this is kind of determined by available compute resources in our hardware. So to help you to understand this concept, let's make an analogy. So let's say we have a tank of water here, and we have a pipe here. So the pipe, the width of pipe is equivalent to the memory bandwidth. And you have a group of people who are waiting for drink waters. And how to evaluate this system? So the system is measured by the total number of water consumed by this group of people. And let's say, what is memory bound? So memory bound is you have a tank of water and the pipe is very small. And you keep the water is keep flowing through this pipe, but because this pipe is too small, which means the bandwidth is too small. So let's say you have 4 people here, so only 2 people can kind of drink waters. And these people, you can assume this is kind of compute resources you have. So this is memory bound, which means more people are waiting for water to come in from the water tank. So this is memory bound. And what is compute bound? Let's say you have 2 pipes together, so you kind of increase your you kind of increase your memory bandwidth. However, you only half of your pipe because you don't have enough people to drink your water. So kind of you are not fully utilize this pipe, and you are not fully utilize this memory bandwidth. And to increase the total kind of capacity or total capability of this system, you actually need more people, right? Because let's say you have 8 people, you can fully utilize this pipe. So this is analogy. So in this region, let's say you have algorithmic intensity somewhere here. So this red region is what we call memory bound. So the memory bound is exactly what I said here in the second case, the second example. And if you are locating in the green part, so yeah, basically is in the last setting I'm saying here. So this is the roofline model. If you know your spec of the hardware platforms, and you know the operation intensity of your algorithm, you will kind of use this rough analytical model to help you to analyze whether your workloads is memory bound and compute bound. Let's say if you found your design is memory bound, you can do 2 things. The first thing is you try to increase your algorithmic intensity, which means you try to reuse more and more data transferred from memory to kind of move this point to the right. And you can also, if you are designing a hardware, you can also try to increase your memory bandwidth. So yeah, so different scenarios, you have different strategies, and this is what we will cover in the rest of this lecture. And here I give an example, a simple example of matrix vector multiplication. So this is one of the key workloads in large language model, especially in the decoding phase, which means we use the causal mask to do autoregressive generation. Let's say your matrix A, you have 4096 times 4096 numbers of elements, and you have a vector, you have 4096 elements, and you do this matrix multiplication, you get the outputs. So how to count this operation counts? So remember in this slide I mentioned on Monday, so one multiply accumulation is count as two operations, right? So for flops, we actually have 2 times 2096 square, we get this number. So which means the total amount of flops we need for this matrix vector multiplication. And in terms of the total bytes to transfer, we need to calculate weights so let's assume weights and activation are 32 bits. And we have weights A, we will have matrices A. This is the total number of memory required to be transferred for matrix A. And we have vector, we have input and output. So we have this number. We add them together and we divided this flops count by this amount of data is transferred. We get this number. We get this operation intensity, for example, is 0.5 flops per byte. And we can find, okay, this is actually in this very close to the origin. So this is a memory bound problem. And the reason why I make this matrix vector multiplication as an example to explain this roofline model is because in the later of our module, we will have a lecture introducing what is the key performance bottleneck of large language model, and we'll realize during the decoding phase, large language model basically is just a memory bound problem. So it kind of drives the latest hardware development of AI platforms. So today is all the content will be covered in our first lecture slide. So if you will remember, in the second half of our Monday's lecture, we introduce this algorithmic basis. We use a single neuron example to introduce what is the forward pass, backward pass, and loss computation, and gradient updates. And we try to scale this single neuron to massive amount of neurons. And we kind of form one neural network layer. And when we try to stack multiple neural network layers together, we kind of form a deep neural networks. And we kind of help you to understand what is the flop counts, how to calculate the flop counts. And the flop counts will be your tutorial questions also. And then we introduce the convolutional neural networks, attention-based neural networks. And the recurrent neural network is just one motivation example we use in this lecture. And the key focus will be attention-based neural networks. And please keep this, remember, in the real exam, we will mainly focus on attention-based neural networks. And we introduce this roofline model to help you to understand what is the hardware characteristic, which type of hardware platform we should choose based on this analytical roofline model according to the operational intensity of the target algorithm. So yes, so this is the first hour of today's lecture. So in the second hour, we will have tutorial. And I believe everyone has access to the tutorial questions, right? So the format of next lecture, next hour, will be we give you 30 to 40 minutes to complete all these questions, and I will briefly go through these questions. The answer will be released to you in 2 weeks' time. But all the answer will be released after the first release of the tutorial questions, so you don't need to worry about whether you have answers. But in the next hour, towards the end of next hour, so I will briefly introduce what is the key points of solving these questions. Any questions now for the module? You think any parts are still confusing to you? If not, we will have around 10 minutes break and you come back, so we start our tutorial session. Okay, thank you.
I have a question for the roofline model.
Yeah.
So, okay, I know the x-axis is OI, and then the y-axis is the performance of FOBs. How do you actually produce a graph? Is it just by like empirical measurements on each independent hardware? Like, how do you know the turning point is at 200, for example?
So, let's say you have a hardware system. The bandwidth is kind of spec provided to you, right?
Yeah.
So if we ask you to draw this roofline model, we will tell you what is the bandwidth and what is the peak compute performance. So you kind of use these two metrics to draw this line.
So you have the bandwidth of a system.
Yes, and we will provide everything and the peak performance.
Good morning. Thanks for the question. My question was between the multi-head and the single-head attention mechanism. So I understood that from a single head, every value is being multiplied and the next value is chosen based on the ranking of the next prediction. The value, like for example, which we took like the didn't, and because it has the most highest value, so we ordered it that way. So I wanted to understand this in a similar manner. What is the multi-head like? We are doing for each head. We are doing again the same calculation.
Yeah, we do the same calculation, but the difference is we have different sets of query key vectors, right? So the computation is the same, but the input is different, right?
Okay, so the input
is different.
So for every different input, we are trying to do
Yes,
again.
yes.
So this will allow us to have a more like advanced output.
Yes, because all these linear layers, they are learnable. They have learnable parameters, right? So for different heads, you can just imagine this is try to capture the different semantic context. Like for let's say for the first head, maybe this is for let's say they just have a different semantic context. Yes.
So this will give us like a better output, but
Yes.
it will be also performance intensive.
Yes.
The next question I want to understand, when we discussed the encoder-decoder architecture, then encoder-only architecture, and the decoder-only architecture, and finally we fixed on the prefix decoder architecture. So I wanted to understand, like, so how will, why did we go from the encoder-decoder to only encoder architecture? As you suggested, that the limitation will be that we need to rely on the context provided by...
Yeah, the key reason for this is we want to have one set of model, just one set of layers instead of two parts, because in your encoder-decoder architecture, you basically have two parts, right? The left part is the encoder, and the right part is decoder. It's not very parameter efficient. You know what I mean?
Yeah.
So they have different sets of parameters. It's not very parameter efficient. So we want to have a unified model for both purposes. Yes. So that's the reason why encoder only with the prefix is a better approach for scaling. Because now you can see the large language model scale up to, let's say, 170 billion. But if you use this encoder-decoder architecture, you might not be able to scale at least this parameter count.
Having two different model architecture and trying to scale as more
exactly. Yes, exactly.
not economical.
Yes.
But if I question that in terms of performance, is that also the same case? Like
so empirical study shows prefix decoding is actually better because you try to blend both encoder and decoder capability using one unified set of layers. They are showing that this is better. Even empirically, encoder only is still better with prefix. Yes.
My-
Because they are trying to learn more rich
because
capability.
they have a capability
Yeah,
of
yeah,
going
yeah,
to
yeah.
previous, and
Yes,
as you
yes,
said,
yes,
they
yes.
also have the capability of fully
Yeah, yes.
visible
Yes.
matrix as well.
Yes.
So that allows that.
Yeah.
And one of the last questions was that the diffusion language models which we had, which so far which I studied was that they're great at image generations and they have performance in doing better. Is that the same case for language as well, like the text modeling as well? Like, do they show the same capabilities in that scenario?
Yeah, as I said, this is very early stage research idea. So people are still exploring this direction. But I think you're right. So text is more like, it's natural, it's more like autoregressive. It's not like denoising process. But for some structured generation, like code generation. For code generation, let's say you define a function for let's say first product. So you can just, you know what you are going to generate. So it's more suitable for some tasks with the structure. You know what I mean?
Yeah.
Yeah, so it shows some capability in some structured text generation.
Is there, I'm not sure, this is now a question, that is there a possible that the logic generation, like how we have the mathematical Olympiads, like the logic reasoning kind of thing, can diffusion models generate those?
Some people are exploring that direction. Yeah. I think in recent months, they are exploring this reasoning ability.
Apart from this, I'm also considering the independent study option as
Okay.
So if you have any kind of projects which are coming up,
Okay.
I would be very happy.
Yeah,
I can email you.
I can email you and attaching your CV. But this year we don't take too many master students because I already took lots of students. But you can email me. If I have any vacancy, I will let you know.
Yeah, I would appreciate it.
Yeah.
Thank you.
Next.
Are there any way you send the materials to me?
Okay. I will try to ask the department. Have one or two students. I will let you know.
Okay, but how about the tutorial?
Oh, tutorial. Perhaps I will send you all the. I will tell you later.
Sorry. I just want to clarify, is our goal from going through these models to basically be able to compute the complexity and the memory of the actual model itself, so that we can then baseline it on the hardware? That's our goal, right?
Yeah.
So, are we able to just based on the model, having knowledge of the model?
You mean a roofline model or the attention-based neural network?
The neural network model.
Oh, sorry.
A model architecture. Based on the model architecture, we should be able to derive what the complexity and the computation is, right? Or we need to know it per model. We have to know the actual formula, or we're able to derive the formula that we can.
Don't worry about this. If let's say in the real exam or in real questions, I will give you the detail of this model.
Yeah.
You don't need to remember what
But you should be able to derive the computational from the architecture.
Yes.
Right.
But I think some basic concept like what is the self-attention, you still need to remember, right?
So you need to know the computation of a linear layer, the computation of an attention layer, the computation of a convolution, let's say. But once you know these building blocks, you can put them together to be able to.
Yes. We will clarify all this information in the tutorial questions.
Okay. And our goal is memory and computation.
Yeah.
Just a question. If there was a case where this was to the power of 3 cubed, and we'd have something in the order of magnitude 10 to the 9, then we'd have the flops per byte to the magnitude of 10 to the 3, right? So if we were to look at this chart, then we'd have to go along the x-axis. And then that means that if it was around 1,000, we'd be at the maximum performance.
Yes. That gives you a theoretical performance you can get. It's not the actual performance. So basically, let's say you got the operation intensity, right? So you plot this. You will realize what is the with all the ideal implementation. What is the peak performance you can achieve? So this is just help you to understand your workloads.
Is the goal to reach this top level? Is the goal to kind of reach maximum performance?
Yes. The goal, let's say if you have an algorithm, right, it's 100 here. your goal is just to reach this point, because this is a theoretical maximum point. Perhaps let's say you have your initial implementation, you have 100, your algorithm operation intensity is here, right? So your initial implementation is here. So what you will do is you do some optimization, like what we will introduce in our lecture. Like we have a GPU kernel, and your initial implementation is here. What you are trying to do is just keep this performance up.
Okay, so hardware design makes your implementation go further to the theoretical line.
Sorry?
Hardware design and hardware utilization makes the actual line go closer to the theoretical line. Is that it?
No, it's the program, your program.
Okay.
Yes, your program optimization help you to reach this line. So once your hardware is fixed, so you will have this roofline model.
Okay, so this is a hardware line.
Yes,
and then
yes.
you have program to get
Yes.
to the hardware.
And what's the difference when you're within the memory bound versus the compute bound?
When you are within the memory bounds, it means your algorithm or the workload you're trying to accelerate will be bound by the memory bandwidth. Okay. So that means you will need to think about how to increase your operational intensity to further improve the theoretical performance.
So in that case, for example, like rather than using more memory, we use more computation. So we do something twice. So instead of being memory bound, we're now like computation bound.
So,
is that the goal?
In
your algorithm?
So, yeah. Exactly. So in your algorithm, you might need to change your implementation to kind of do some more data reuse to do more computation. To kind of push the operation intensity to the right of this.
In the algorithm you said this with the vector matrix multiplication, then it happened to be run here, right?
Yes.
But if we did matrix inversion, which is n plus squared, then what would happen around here? So there is something like
Matrix conversion.
Inversion, like
Inversion.
compared to matrix.
Yeah, it depends on like the operation counts and the memory access you need, right? It depends on the algorithmic intensity. You need to calculate the algorithmic intensity of your inversion, matrix inversion. Yeah. So this roofline model is just a guide. It's just help you to understand. Let's say if I have a very perfect implementation, what is the peak performance I can achieve? Let's say if you realize your workload is memory bound, it means, for example, if someone sitting here, it means it doesn't matter how your code is optimized. The peak performance will be just 0.75. And if you want to further optimize the performance, what you need to do is just what this says. You need to change your algorithm, try to reuse more data, and try to improve this algorithmic intensity to push it to this region, to make it as compute bound. Do you know what I mean? Yes. It just kind of provides you some guidance of how to design your algorithm and how to improve your kernel. Yes.
Yeah, thank you very much.
You repeat what the limitations of the encoded architecture.
Okay, so the drawback is they kind of keep two parts of layers, right? They have encoder and decoder. It's not very parameter efficient compared with the decoder only with prefix. Right? This is the first reason, not very parameter efficient. And the second one is empirical study. Let's say from Google T5, the paper I attached in this slide. Decoder only with prefix actually performs better than encoder empirically, because they use one set of models to learn different probability for understanding in a generation. And some study finds learning these two different probabilities in one model, one set of models, is actually beneficial. They're using two sets of models.
Yeah, that makes sense.
Yes.
Also, is the exam open book?
It's closed book. It's close to, and but you are are you through undergrad?
No.
Okay, okay. So basically, they allow you to bring one page of A4 the paper into the exam. I guess you can write down something into the imperial student. Yeah. No?
Yeah, I'm master's student.
Oh, you're master's student. But yeah, this is what they.
Like double-sided.
I think it doesn't matter, right? I think you just need to write the front very small.
Yeah.
Okay.
And then also, so like, to what extent can you make up for some like architecture being memory bound by increasing it?
Say it again.
To what extent can you improve like if you have an architecture and it's memory bound? Is that
No. Architecture, you cannot say architecture is memory bound.
the model?
Model, yes.
Yeah. So, like, how is there any extent to which you can improve that by improving the compute?
Yes. Let's say you just try to reuse your weight matrices to do more computation. This is one way to move from memory bound to compute bound.
Thank you.
My question will be about like this really interesting model for me, but to choose it like in the first or like in the first slides, the attention mechanism I like learned before, but it depends like their formulas. Like how much detail in this introduction should we know about in the next slides?
Okay. So your question is how many
Like there are lots of details. Do we know that much deep or like should we focus on?
No, you basically just need to know like I think 3 basic layers: fully connected layers, convolutional layers, and attention-based neural network layers. Just these 3 layers. For the other things, you don't need to worry about.
So like should we focus on more on these sections, question and answer session?
Yeah.
I'm a bit worried because there's so much content.
Yeah. Okay, I will explain later. So basically, I put a lot of other content here, like the diffusion language model, but this is just for more ambitious student who wants to know more. But I think the basic is still. Yeah, the basic is still like, as I said, you need to understand what is the computation of linear layer, fully connected, that's the first one. The second is a convolutional layer, and the third one is the attention-based layer. So these 3 layers, and for the other advanced knowledge, you are not required to understand, and they are not related to or required for following lectures, and you don't need to worry about.
For this like what should we know?
You mean Luftline?
Yeah,
Luftline, you need to know everything.
every line here, right?
Yes. If you want to know what is the focus of our exam papers, always look at the last slide, the recap. I will summarize what is the key required. For example, here I push you. Basically, you need to know attention, and attention masks, including the lecture, the Luftline model, convolutional neural networks.
Yeah, you also said in the first lecture the questions will be from the question answer
Yes.
Like, what does that mean? Like that question similar to that ones would come up in the exam slide.
Once you can independently answer these questions, you will find with most of the exam questions, because I will give the very similar exam questions to the question you have seen in tutorial.
Okay.
Yeah, thank you. I will explain more later.
I just had questions, 2 questions. One for the depth-wise convolution. What I'm not understanding is we're not working in the same channels, right? So each one has their own filter.
Yep.
We have same number of channels, same number of filters.
Yeah.
Then does the height out, height in, or sorry, the height out, I guess dimension out, excuse me, does that formula still carry over from the original convolution? Because you're still getting effectively the same volume on the output.
Mm-hmm.
Is that the same kind of formula there for, like if we go back here, there? Is it like essentially a similar formula?
It depends. I think it depends on the setting of your convolution, like
Okay.
whether you have padding, where
Yeah.
have you stride,
And then with the padding terms, we just add I think it's like plus 2p and then over s.
yes.
And then only other question was for the scaled attention. When we mentioned like the decay, it's the internal dimension there? Is that correct? Awesome. Thank you.
So I was a bit lost in the lecture today. I'm just wondering if you have any recommended video.
Which part you are lost in? Starting which part? Attention.
Do you have any recommended book or
I can give you this one. This online source. You will understand everything. Yeah. It's the page 34. You have access to the slide, right? Yeah. Just look at click that button. The button will give you link to your.
Yeah, I just want to say a quick reminder. Like my friends are like thinking the same way. Like you can make a clarification for the whole class. If you want, like it would be beneficial, but I just want to notify that on my previous questions.
What do you mean? So I don't.
Where to focus on more, like you said, you are going to make announcements.
Yeah. So you mean they are not here now?
No, they're here.
Oh, yeah. Do you want me to make clarification now? Right?
Yeah, if you want, like.
Okay. Got it. Yeah, I will do it. Yeah. Overflow.
4 people, and it's only overflow, and they all be moved to here.
Okay, got it.
Next lecture.
But do you have the? Do I need to set the permission when you play video?
It just plays.
Okay. That was just everything.
When you start, everything starts.
Great. Thank you.
Next time we don't have in this room, maybe we can cancel.
Yeah, but yes, I think the overflow is.
Come back to it.
Yeah, where for the question next time? We could just say okay.
We'll wait for the next lecture. That's how people try to decide. So are you? You did, yeah. I didn't get to.
Just some common questions I received during the break. Hi everyone, just give me a few minutes. I collect some common questions during the break. The first one is some people are saying they kind of lost in this attention part. So in page 34, if you click this link, it's a very, very good online resources for you to understand everything. They also have animation and some of the course materials actually adopt from here. And we also put a reference. This is the first one. And the second one is some people are worrying about this is too content heavy because we introduced so many models. So what I want to highlight here is you don't need to worry too much about like Mamba or other advanced efficient model variants. In this lecture, the deep learning basis we want you to have is first, you need to know what is, they are actually already listed in this recap slide. What you need to do is you need to understand what is forward pass, what is backward pass, loss computation, and what is training inference from single neuron to like multi-layer perceptrons. And the second is you need to understand what is the convolutional layers. Let's say in one of our tutorial questions, I asked you to calculate the flop counts of depth-wise convolution. So you need to understand how to calculate flops for convolutional layers. And the third part is attention-based neural networks. You don't need to worry about diffusion language models, members. The key is you need to understand why we have attention. So that means that corresponding to the last question of our tutorial questions, what is the advantage or disadvantage of recurrent neural network and LSTM over attention? And what is the self-attention mechanism? This is the only part you need to grasp after this module. You don't need to worry about too much. And even for later lectures, you only need to know like attention, these three parts. You don't need to worry about member or diffusion language model, just the basic mechanism of attention mechanism. It involves like self-attention and how the computation is done. And the last part is the loop-line model. So the loop-line model is very important. I would definitely ask questions in exam on loop-line model. So ensure you understand this. And for the loop-line model, it's basically, as I mentioned before, served for two purposes. The first one is if you have a loop-line model for your target hardware platform, and you once you know what your hardware looks like, let's say you have the specs of your hardware, so you can draw this plot, right? Because you know what is the bandwidth of your target hardware, and you know what is the computational capacity, which is the peak flops of your hardware. You can easily draw this. And the first purpose of loop-line model is try to help you to identify whether your workloads is memory bound or compute bound. Let's say you have an algorithm. So let's say you have depth-wise convolution, and the operational intensity is this. And you write a kernel, let's say GPU kernel, and your flops, your performance kind of somewhere here. So what you can do is, without changing hardware and without changing your algorithm, what you can do is you try to push this dot up. So you can apply what we introduced later. You can apply memory coalescing and kernel fusion. What you can do is just, if you don't change hardware and algorithm, what you can do is just push your implementation up to improve this performance. This is the first purpose of loop-line model. It helps you to understand how far your implementation is away from the theoretical performance, which is actually this point. This is the first purpose. So if you are a kernel developers, so this model will help you to see, okay, I'm in the memory bound region, and how far my implementation is away from the peak performance. And the second is if you are an algorithm developers, let's say you are allowed to change your algorithm. The other thing you can do is you can try to increase this algorithmic intensity or operational intensity. In the example of depth-wise convolution, let's say you try to reuse as much as weights. So you can actually improve this algorithmic intensity. So you try to push this line in this direction, right? And perhaps you can have some implementation in here. So this is the second purpose of loop-line model. It kind of, if you are designing an algorithm, it can help you to design a better algorithm with a better performance. And the third is, as a hardware developers, you will kind of know, let's say, if I have this kind of loop-line model, how should I change my architecture to kind of make, for example, make this vertical line higher, or kind of make this slot line more kind of with a steep, like you can kind of under the same operational intensity, how can I push this ideal performance? So this is the three purpose of loop-line models. And one thing I want to mention is once your hardware is determined, this loop-line model is determined, you're not able to change this. This is just help you to guide your kernel optimization or your algorithm design. So yeah, clear? Or any more questions on this? If not, just continue your tutorial questions. And sorry for the interruption. And I think all our RAs are already here, so just raise questions anytime you have.
notation 有点不太统一，所以有的时候看的就是可能会有一点 confuse， 因为这些都是就是矩阵矩阵乘法，这类的嘛。然后你有的地方写的是新，有的地方啥没写，有的地方写的是底。
对，我觉得这个可以，就是你们做的 math 的会比较 sensitive。
对，就整节课如果都是统一的话，可能 less confusing。
好，我之后其实我自己也想过，就是要统一的 notation。
对对，不然的话就是前面和后面会不太一致，然后就有一点
对，明白。其实这样会让那个他们如果没来的话，然后他们看这个 slide。
对对，因为我其实也是上课的时候才，我看的时候其实无所谓，上课的时候哎，怎么看不一样？
是的。
Each token generates one unit words, and then each of them undergoes a translation, or in this one, and then you do the self-translation, and then you end up with soft.
Yeah, I'm actually. We're just about to see the explanation from I mean the thing is that there is something but we still like different terms for each term.
So this is just a soft max over all the possible output columns. And then you choose one. And so this one is one thing about that. This is generated from one token. One token generates one value, one key, and one value. How do we get multiple linear layers for each value? I mean, you have all those pieces. That's why.
Each channel has a filter, right? And that's all filter. In terms of the operating system, how many bytes?
So the number of filters and the number of channels will always be.
So for one sentence, for example,
so maybe number that your base filter will be double or could be and filters are different for each channel.
Third word of each of those sentences to generate like a value query for each of those, and those are you generate some sort of linear output. I don't know then you have and then all of the generating values get query and then you
Why do you need it?
So one of the students asking, like, apparently they're missing a slide where you showed an example calculation for the transformer. Maybe it was something you drew on the slide or something, but he's asking if you can put it up again.
My question is,
I don't think we have the.
you would have the token didn't, and you would create that. Let me check. And then you would this out. And here, what's up with multiple?
Imagine doing this. So you would have
Yes.
one
For a head?
Yes. That's why you need to do it.
And what is the head that is?
Imagine this as like I have a sequence, I have different ways of understanding.
So one of those can show the
Just like this one head. That's how like one has showing attention to the reason why we have each has to understand the same sequence. So to give me the calculation as much as happens now is just one one way to be able to see the understand. Here you have multiple. That's why you will be
With the weight matrices different for the same beam?
It's an extended dimension. So you would have a weight matrix for B anyway. One is self attention, but you have only one of them. This is just one is the function, so you would apply it on the B times to get like a but if it's a 3D matrix.
Okay, so here you take the thin, and you just do one matrix multiplication of them, and then you do subtraction, and then you get the big. Here you would take the word here you would take thin, and you would generate one value into the query, and then you would multiply the sample with, let's say the parallel dimension here is 3.
If you're at number of hands, 3.
Yeah, then you would have 3 different matrices.
Yeah, you're often one vector. That's one, 3, that's 2.
Okay, so
you subtract not only like you do one subtract each step.
Okay, so for this one, if the dimension of the matrix here would be 3 times, it would be 3 times as many parameters. So you would still only train, you would still train on the same input and out the same output.
It's not really, I mean, yeah, so I'm saying we use the same.
Or should I wait for them?
Sorry?
Should I wait for them, or can I ask you?
Oh, yes. Is the depth-wise clear too?
Yes.
Sorry.
Yeah, it was. Thank you. So I don't understand this.
Oh, still don't understand.
No. So I understand what operation per second is, of course, or flops per second, and this is operations per memory byte access, right? Okay. So imagine I'm doing, I don't know, one operation per memory byte access. I'll be here.
Yeah.
So why is this line like this and not like this and not like this? Why is it a straight line? Who is defining this graph? I don't understand.
Let's say you have one okay. Your question is about the slot line, or is the?
So is this just the representation of a particular hardware?
Yeah.
If we have another hardware, this will change, right?
Yes.
And this slope is determined by the bandwidth.
Yeah, of your hardware.
Of your hardware. Okay.
So each different hardware will have different.
Yes, but
so basically, it helps you to understand what is the theoretical performance you can achieve of your workload. For example, if your workload is 100 ops per byte, so you draw a vertical line, and you can see this cross point, right? This cross point is exactly what you can achieve.
The number of operations per
yes,
second.
Yes.
But
the peak performance.
if I have 100 operations per memory access, then I get it. So if I have 50, it's not that the hardware is less efficient, it's just I have less operations per second because I'm doing less operations per byte, right? Or no?
Yes, because you're doing less operation per byte and the peak performance is decreasing.
Okay. Yeah, I guess the word performance was kind of misleading for me because it's the same efficiency, it's just less operations per second because you are doing less.
Yes. You can just assume this as an two extreme case. Let's say you have matrix multiplication, it has a high algorithmic capacity, and you try to make it as matrix vector multiplication, it just performance just goes down because it falls into the memory bound region. And when you do the computation, it's just your compute resource is always waiting for the model that come in, but they are not coming in a very fast speed.
So that's why performance goes down.
Yes, goes down. Yes, so this is the reason why. So I thought I'm using this water tank and pipe things will help to explain. So you still don't understand?
No, I understood now. But and then when you reach 200, you also here is the limit of your computing resources. Okay.
Yes, and then it was part.
And then here, is there a difference in performance between doing 600 and 500? There is not, right?
The theoretical peak performance is the same for 500 and 600.
So here we cannot optimize anything.
Yes.
We cannot.
Yeah, cannot.
But here we can.
Yes.
But you mentioned an example here that we could optimize up to here.
Yeah. But no, if let's say you have your workload is compute bound, sometimes because your implementation is less optimized, you can still fall into somewhere here. You can still push up.
Okay, yes. I understand. And you can only push up until here because then you don't have more compute.
It's just they just define the region you of your max performance.
Okay.
So, for example, if your let's say you have just so that you can make that your input time needs to be the same as this you don't have. So just have the same input, the same output, just find more relationships and you're not chunking your sentence you're trying to connect with smaller
this one, the question arose by
so you don't have this
I'm not familiar with
No, I think that's someone else. Yeah, but that's fine. They're wondering the number of weight parameters. Yeah. So, yeah, there's like a couple of politics. To me, it seems like they're all square feet basically with like one other thing that's all like, I mean, the good thing is you can set your data loads plus one of those. Seems like should be that. So it's yeah, on the company. So, right, I think it's maybe the architecture is kind of that's a very more. This is not. I mean, it's like carousel style architecture. Carousel. So it's like disconnect the update pods you have and pressing it. So you can kind of like send something to Spotify and collect this output later, and then once it's kind of going to. It's kind of good because it gives a lot of architects try to do this, but they have too much writing, which makes it like so you can schedule these down for the same amount. It's going to be so that's why it's good for everyone. Let's just call it now, I find it interesting how they use the because that's signing the box right. So that conversion is that done all one? Is that like the thing about fusion is so the main point of that project is like if you know like okay, fusion it has like maybe for example 9 inputs and use one of them. If you are very this is like like each of the externals there, something like that. So it's latency, which is actually quite small. That means they have not like 9 inputs at the basically a massive amount of inputs at the beginning. So in a data flow, like this, send inputs in and input should be really slow to make sure there's no backpressure. So one experience like I want some backpressure. I don't think these data flow like series are good if you have very, very like high state dependency where like one outflow it's like it's really slow. I think the way to overcome it is smaller, but make the inputs very slow. So the inputs need to be, and the hardware can be slow. So it's basically no back pressure, and it can still do the output the same. The other one is
If you have a J, you know that you know not
And then
just roughly. What is that for you?
so what's that one? So when I came up with the, so I suppose, for example, it's not necessarily like goes from to it, like learning to think about actual multi-themes, it's like very, very detailed dimension. And with this like, how they, it was hard to design like much simplification. I'm just wondering if that you have, which is more milestone, basically always this back that you need to just that. So my theory was, okay, well, this is balance of that, to make sure it's like no matter but the dimensions of the internal experience, there's too much data to get balance
I guess it's really
then basically and forming on basically this one. But then what does it say that you can be and then oh, I know. Because I thought this layer was yeah.
Yeah, I think it's something that later on. You know, I was just kind of like a beginning of my third year. Yeah, so the first beginning of my
yeah, so
So I heard some companies actually doing like data forensics. Like, are there companies? So obviously GPUs
No.
This is in your I wouldn't call it that is not existing course. Yeah. It's like a the linear layer is kind of before that.
Yes. Yeah, I will go over. It won't be like explaining just the key point.
Yeah, so these three, right? So you have the one X, but then you look at three different different projections.
And then they would be directly
Hi everyone. So we only got I think 5 minutes left. So I will just quickly went through it. Go through it. Before I start, any particular question? Do you think this is too difficult or should be manageable? Okay.
I think it's difficult if we don't have a clear reference. For example, convolution. Like we don't know whether the bias, how many biases there are. For example, like if we had a mathematical definition in the slide for what we should be using as reference, I think that'll be easier for us.
Giving a formula for
yeah, so that we don't need to bring so much additional knowledge from
Okay, got it. So I will try to update. But what is related bias? I think,
So for example, the convolution question, how many biases should we have, for example? Like we need prior knowledge to know, okay, one bias per filter, for example.
Okay, got it. Okay, so I will update the I will update the slide to explain this for each. Yes. And apart from
some kind of standard number of flop counts for the kind of compound things like exponentiation or when you're dividing. So it's not just one.
Sorry, say that again.
So
for softmax, right?
So like addition is just one flop, sure, but exponentiating a value.
Yeah, we count this as one flop.
So we just count every single equation.
Yes, exactly. Yeah. So and we even for exponential, it's just one flop. Just to make it simple. So for go ahead.
Sorry, just kind of on the same question there. Is there a bias in the CNN?
So if what I didn't mention explicitly, there's no bias. So yeah. Okay, so let's just go over this. For the first question, I think I put the formulation in the slide, right? So to calculate the flop count loss of depth-wise convolution. So the key idea is you need to understand what is depth-wise convolution, and there's no channel accumulation. And here we assume there's no bias. And for example, in our exam questions, I will clarify this. For example, I would say there's no bias here to make it clear. And for your question, if later on you can put in the stamp system, I will have good, and I will have to clarify. And for the how about question 2? For the linear projection layer, they basically have just matrix multiplication, right? So you just need to multiply the dimension of these matrices to calculate the flops for each QKV. And this is the same for attention. Attention score, you need to multiply Q with the K transpose. For yes, any particular part of question 2 you are very confusing, or you just I need more. You want me to put more formulation into the slide of attention part to explain everything.
Yeah, like the matrix.
Sorry. The output projection.
Not with the computational cost of full attention masking causes.
Okay, so the full attention. So if you look at, I have a attention mask slide, right? So in full attention, you basically in the full attention, you basically have okay, doesn't work. None of them works. Let me just put my slide. So this is attention mask. So basically what I ask here is just to calculate a valid operation here. So we don't calculate the flops required to calculate this mask out elements. So basically here is, let's say the input sequence of is n. So the algorithmic complexity is L, and the algorithmic complexity will be L squared. But in here, it will be 1 plus 2 plus 3 plus continue L. So this is what I expect you to answer.
Does the system automatically stop calculating after you decide the negative, or will it continue doing the calculation?
Say it again. What's the question?
Because the mass is n by n, right?
Yeah, yeah.
So does it automatically stop calculating once it hits the negative infinity, or does it check for every value and then change the zero? Does that affect the mass?
I think it depends on how you implement, you know. So yeah. So basically, for softmax, okay. So for softmax, they usually do row by row. So they do a softmax, row by row. So yes, they will find. So the question is whether it will stop calculation or.
Because it's the rest for the white cells and negative differentiation.
Uh-huh.
Will this still be considered in the calculation itself, like recalculate each white cell also?
Yeah, it depends on implementation. In some optimized implementation, they will just take.
Then wouldn't that affect the flux count also?
No, because they set the SD negative. Okay, this is a good question. I think. I think I've seen both. I think I see both implementation, and they have different. As you said, they have different numerical outputs. I will post in a different implementation in our app system and reply and send it to you.
So, how do we understand how to calculate the flux of the softmax? Like exponential.
So which part?
In the one application, you have to compute the softmax of matrix.
So which question?
In QE, in value aggregation, you
Yeah,
have
value
to
aggregation,
softmax,
yes.
right? So I don't understand how you compute the amount of flows that an exponent does.
Okay. So you are saying you don't understand how we calculate the softmax.
Right, how many flows is it E squared, basically? Like in softmax, you're exponentiating numbers.
Okay. So sorry, I think this question is a bit confusing. And thanks for pointing this out. So here in value aggregation, we assume it's after softmax. So
Okay.
so the value aggregation, we assume this value aggregation is just after your scaling, after your softmax, you get a vector and you to multiply this vector with your value. You basically just need to calculate the blocks of the matrix. Yes.
On the vectors.
Yeah, I'll make it clear.
Okay. And we don't actually know how many flows the softmax does.
That is the question later, right?
Okay, and how we do that?
Okay, so I think I explained in my lecture slide, right? We have a lecture slide to explain how the softmax is operates. So basically, you will need to first determine what is the max of. Let me just quickly. Yeah. If you are able to refer to this slide, you can see it. So in here, oh no, it's here. The softmax. So basically, you will have is, let's say the exponential is one operation, and you also need to count as the subtraction, and you have these summation, and you have division. So you just count each operation. How many times you?
So exponentiation is just
one. Yes, I explained. Yes. Oh, okay. I think the other student asked this question before. Okay.
So I think that the confusion in the slides. So in the slides for the attention part, like we use right multiplication of the query, the input query to the matrix. But in some of the slides, so for example, in the link that was sent, right, it's actually left multiplication, and I think that changes the dimension.
Yes, I think this is something I would need to unify in my slide, the mathematical formulation. So this is another thing. I will do it. Yeah, okay.
So when we're doing flop counts, things like this, so what level of accuracy do you want to, like a summation, for example, is if you've got 64 length vector, 63 operations.
Yep.
Do we want 64 by 63 by 64? No, are you happy with just like order of 64 cube, for example?
I don't understand.
So like when we're doing flop counts,